Right. So today we will focus on
Recording
AC.
in progress.
Today we will focus on AC applied to series LR circuits. In our previous class, our major focus is on pure inductor, pure capacitor, and pure resistor. Our observations are very clear. In case of pure resistor, voltage and current are in same phase. Whereas in case of our pure inductor, voltage leads current by pi by 2. Whereas in case of capacitor, current leads voltage by pi by 2. These are our observations before I start this. In fact, before I start this, I would like to add one more small theory. Let me work on that. And what is that theory? Anytime we have noticed either the current is leading the voltage or the voltage is leading the current. In fact, we have dealt only pure R, pure L, pure C only. But usually you will have combinations. For example, for a while, assume that this is the voltage phasor. And this is the current phasor. And let phi be the phase difference between the current phasor and the voltage phasor. Remember, when you resolve this into components, this term I sin phi is having a meaning. This component is called wattless current. Because due to that component, there is no loss. There is no loss because voltage and that component bears an angle of 90 degrees. So power is dissipation due to that component is zero. So your major current, your major power consumption is due to that I cos phi component. That is the reason why power is equal to voltage into current into cos phi. Later, for average power, you will write the same as VRMS, IRMS, cos phi. And this is a constant for a circuit. So long you are not changing L, so long you are not changing R, so long you are not changing C in that particular configuration. And this cos phi term is what we will call as power factor. For a pure R circuit, power factor is 1. For a pure L circuit, power factor is 0. For a pure C circuit, power factor is again 0. Because you know pi by 2, pi by 2. So the current in a pure L circuit, the current in a pure capacitor circuit is basically wattless current. Cos phi 0. What is happening in a capacitor? Tell me. No. You should reduce the level of that thinking here. You don't take, you are very much focused. Instead of photograph, you will get skeleton. You are trying to zoom as such that you are not taking the photograph. Finally, you are taking the skeleton of the person. And you show that no one will pay for you. Oh, what is that we have learned yesterday in a pure capacitor circuit? Voltage leads current by pi by 2. No, I leads are right. I leads V by pi by 2 in a pure capacitor circuit. Whereas in pure L circuit, V leads I by pi by 2. You learned yesterday. Correct or not? That's what. Leading pi by 2 means cos pi by 2 is 0. Phase difference. Now I am applying AC to a pure LR circuit. Please follow carefully. Of course, they are in series. We will deal parallel at the end. See, I am not sure. Till now in IITs, never it happened. A parallel circuit was given. Particularly AC. Not, we must be cautious. Inductor, resistor in series. See, try to please understand what is happening here, honestly. What is happening over here? You are applying V is equal to V naught sin omega t, that is the source. Try to please understand, use a phasor in this situation. Suppose if I am taking the VR as the voltage drop across the resistor, and I as the current drop across the resistor, current phasor. You already know the voltage across an inductor leads the current by 90 degrees. What is this vector? Applied voltage. That's the applied voltage. And the applied voltage leads the current by 5 in this case. And remember, tan phi can be written as VL by VR. I into XL by I into R. Omega L by R. That's tan phi. That is the tan phi. Omega L by R. And you can find cos phi also. Why I require cos phi? You already have an idea. That's the power factor. And remember, if I draw the same thing in terms of resistances, for example, this is as same as omega L, and this is as same as R. What is going to be the resultant here? Z. The total impedance. So don't write R1 plus R2 here. I said that is for linear circuits. This is not linear. So therefore, Z is under root R square plus omega L square. There is another methodology that follows in AC circuit representing the impedance as a complex number. I repeat, there is an activity in AC circuits that we represent the resistance in a circuit by a complex number. For example, you know a complex number Z can be written as A plus JB. We are not using I here because we are using I for the current, where J is So obviously magnitude of Z is under root A square plus B square. So in this, A refers to the real part. B refers to the imagine, if I am not mistaken, complex numbers, I think it is not at completed, right? Imaginary. In this case, when I am writing real part means this is ohmic resistance. When I am writing the imaginary part, I am writing, don't say non-ohmic. There is another resistance in AC. What is that called? Reactance. Reactive part. For example, for a pure resistor circuit, Z is R. For a pure inductor, this is how you will represent pure inductor. The plus sign indicates always voltage leading current. If I am writing plus, the plus sign indicates voltage leading current. Now, can you please help me in writing pure capacitor? This can be written as the minus sign indicates voltage lagging I. So till this point, any student having doubt? Standard. That's standard. Okay, that is representing a resistor, a impedance. Z is called impedance. So what is impedance? VRMS applied by RMS is impedance. Okay, any doubt till this point, boys and girls? Any doubt in this part, boys and girls? Any doubt in this part, boys and girls? And now the power at an instant is current into voltage. You know that? And we know this is not pure L or this is not pure R. But one thing I have noticed that the voltage leads the current, that's for sure. So when I'm writing current function, I should write sine omega t minus phi because I know the voltage function has sine omega t, right? So from this you have power, this is instantaneous power. What you are writing here is instantaneous power. Any doubt till this point? Right. మరి దీని సైజ్ తగ్గించలేరు, మరి ఎక్కువ కనిపిస్తుంది అని డౌట్ నాకు. నో ఐడియా. ఓకే, చూడండి, నో ప్రాబ్లం. Right. Now, why? Because, yeah, this allows me to understand the average power. So, I have integrated average power. You can see that average power is what I have integrated between the limit 0 to t. By doing which, I'll get finally in terms of cos, which I already introduced you earlier in general. VRMS, IRMS, cos phi. Here the power factor is what we will call as the power factor is cos phi. From this you can write cos phi as R by Z. Right. So see, at any instant now you can write P instantaneous is 1 minute. From the diagram, P average is VRMS, IRMS, cos phi. There is a power triangle. This is called power triangle. Actual power average is of two components. VRMS, IRMS, cos phi. This is the dissipating one, which converts to heat. And that component which do not converts to heat, which is wattless, is VRMS, IRMS, sin phi, which I have already introduced earlier. And this is called wattless power. This is not a loss. This is not the loss. The average energy stored or restored. Okay. So finally, what are our conclusions in a AC applied to a pure LR circuit? Voltage leads current. Z is under root R square plus omega L square. And by the way, average power is also given. Phasor diagram is also given. As I told earlier, the voltage is leading current. So I will have two components, I cos phi along V, I sin phi perpendicular to V. This I sin phi component is called wattless current. Now I am applying AC to a CR circuit, which means C and R only in the series. Obviously, in this case, not much of mathematics is required. You will write the impedance in the form of a complex number like Z minus R minus sign indicates voltage is lagging behind. In this case, what will happen is, this is how VR phasor is represented, and this is how VC phasor is represented. Because I know if this is a current phasor, the potential drop across capacitor lags behind by 90 degrees. But remember, this is VR, this is VC, and their resultant is V. What is that we applied? So from this, you can get Z copy as what we have done previously. Only in the place of XL, you are writing XC. Again, the same power average, VRMS, IRMS, cos phi. Boys and girls, any doubts? Any doubts? Okay, the one which we have covered is LR circuit. The one which we have covered is CR circuit. Any doubt till this point? Boys and girls. ఉంటుంది but see total power loss in a AC circuit, DC circuit is simply V into I. Why not it is V into I in AC? Because that V into I has two components. V into I cos phi, which is accountable under dissipation. VI sin phi is not accountable, and it is not a waste part. It's stored or restored. Sometimes it's in the form of energy stored in the system in a different form, or sometimes that is same given back to the system source again. Any doubts? Right. Now, what about AC applied to a series LCR circuit? When I am applying AC to a series LRC circuit like this, multiple cases, in fact, 3 cases are possible here. Let us see the cases individually. Now, first thing, confirm me, are you convinced with this Phasor diagram? Everyone in the class, are you convinced with this Phasor diagram? Everyone in the class. Convinced? Right. Now, do you have any idea prior to starting the problem? No, I don't have any prior idea. I might feel that see, I will assume different cases like this. I am assuming the inductive reactance is greater than capacitive reactance. Case 1. Otherwise, inductive reactance is less than capacitive reactance. Otherwise, inductive reactance is equal to capacitive reactance. These are the only 3 possibilities. You have nothing to do with R, by the way. You have nothing to do with R. Right. What happens in the first case? See, in the first case, if XL is greater than XC, in this case, the resultant phasor becomes R XL minus XR Z. In this case, voltage leads current by phi. Agreed? XL minus XC. Whereas on the other hand, what you will say, right? I leads V by phi. V, remember, is applied. I, the total current in the circuit. I refers to the total current in the circuit. Any doubt? Sure. There is one case. It happens only for a particular frequency. Because don't forget, XC is 1 by omega L 1 by omega c XL is omega L. It happens for a particular frequency called resonant frequency where omega naught L becomes 1 by omega. At that frequency, you know what happens? VL becomes VC. At that stage, current is maximum and power factor is maximum. Why current is maximum? Resistance is least. Impedance is least. Impedance is least. For the same voltage, current will be maximum. Remember, it won't happen every time. It happens only for a particular frequency, and that frequency is called resonant frequency. Okay, na? Now, from the graph, you can see if I have plotted the current Mahalakshmi, Nidrabhatana, the power, the current along y-axis, omega along x-axis. You will get a graph like this. Remember, you have two graphs. Notice one is blue color one, the other is a light dark color one. So in this, what you will notice is one is the graph for very low resistances. Two is the graph for relatively higher. As the resistance increases, you know the peak sharpness come down. What happens when R tends to infinite? R tends to zero. Infinite current. Same thing you observed in damped oscillations. Not damped oscillations, actually forced oscillations. When we are studying SHM second degree, we have studied this. Now, what is this equation at an instant? Please see. Is this not the equation LR circuit, LCR circuit? So how this equation look like? It is like similar to M T square x by dt square plus B dx by dt plus omega naught square x is equal to F naught sine omega t. Forced oscillator equation. In forced oscillator, what we have noticed? When the applied frequency is the same as the natural frequency of the oscillation of the body, amplitude is maximum. And that condition is called resonance. So therefore, here also you will see a resonance. At resonance, try to please understand the source, the potential drop across the source, the potential drop across the resistance is the same. Do you want me to repeat? The potential drop across source and resistor is the same. The voltmeter, if connected across the source, it will show the same reading across. Why? Because across across L and across C, their combination gives 0. Any doubts? Any doubts? Any doubts?
రెసిస్టెన్స్ తక్కువ ఉంది కాబట్టి కరెంట్ మాక్సిమం ఉంది.
రెసిస్టెన్స్ తక్కువ అవుతున్న కొద్దీ పీక్ మాక్సిమం అవుతుంది.
మనం SHM లో మనము యాంప్లిట్యూడ్ పెరుగుతుంది అని అన్నాం కదా సార్. ఇక్కడ ఏం తగ్గుతుందో మనం
యాంప్లిట్యూడ్ damped oscillations లో HC వర్మలో you have one equation related to this amplitude.
సార్ రెసిస్టెన్స్ ఫ్రీక్వెన్సీ యాంప్లిట్యూడ్ పెరుగుతూ పోతుంది కదా సార్ కంటిన్యూస్.
ఏది?
రెసిస్టెన్స్ ఫ్రీక్వెన్సీ.
అవును, ఇక్కడ కూడా ఏమవుతుంది? when R becomes 0,
కరెంట్ అనేది మాక్సిమం వెళ్ళేది లైక్ ఇన్ఫినిటీ టెండింగ్.
that's how it becomes. Remember, this is graph. You are studying I as a function of omega. Okay, so in 1 minute, in damped oscillations, లేదా అది నోట్స్ యాజ్ ఆఫ్ రెడీగా. So in damped oscillation, H.C. Verma, there is one equation related to the physical case. Amplitude terms lo untundi adi. Unda? J0 group level. Yes. Yes, obviously. XL is equal to XC, there is no reactance. Total waste. Total power is waste. Cos phi 1 means there is no wattless current in this case. Everything is waste and converting to heat. Where n number of cycles happens, it gets converted into heat. Right. So that part we will work again. No, please, this is, remember the entire thing what I have written is NCERT. You don't require to go through NCERT. Just please read this. Just please read this once. Everyone try to please read this. Resonance circuit has variety of applications. You are asking me the day one why we require capacitor. I said wait. When I started inductor, why we require inductor? I said wait. Now what is happening now? All your tuning instruments like radio, TV, even what do you call walkie-talkie phone, they work on this principle. See, for example, I am speaking via a radio channel, say 93.5 FM, for example, that's broadcasted in the around the area of Hyderabad. Say, for example, that takes a range of 30 kilometers. So long when I'm in 30 kilometers, when I am tuning my set will have a different natural frequency on the basis of the capacitor and the inductor what I am using. For example, my 1 by root LC will have a different value when compared to the FM station. So the only thing what I have the option is to change capacitor. While turning a knob, you are changing actually the capacitance of the arrangement. So by turning the knob, I am changing the capacitance and hence I am changing the resonance frequency of the circuit. When my natural frequency, my LC frequency and the radio FM frequency matches, when my antenna receives this, that one will have maximum current. And Baki sub reception is not that good because earlier you studied sound waves, you have studied one thing. Some detectors will detect only amplitudes of so and so range. We have done some problems also in that. So when this frequency related amplitude is high, that is very clearly recepted by your instrument. And that is what you are listening through that particular device. Similarly, that's what clearly described here. Just please go through this. NCERT, very, very important term. NCERT based, very, very important term. Because the same thing will be given in mains examination also. See, for this equation earlier in SHM, we have written the amplitude as F0 by under root m square omega square naught minus omega driven. Actually, this has a driven frequency. Plus omega driven square b square whole power 1 by 2. That's the amplitude. Remember, I am not teaching anything related to LC now. I'm just trying you to memorize the conditions which I have defined there. Okay. So, what the condition we require is when the driving frequency is close to natural frequency. When omega d almost same as omega naught, the amplitude will now tend to f naught by omega dp. Now the problem is in the denominator, the term is B, damping thing. What is B in our circuit? Which part of the element is close to representing B here? Resistance. So more high is the resistance. More is the damping in our physical situation. So therefore, as you increase the resistance, what happens? The quality factor comes down. The sharpness will come down. Okay? Right. So therefore, this is introduction to series LCR circuit. Resume
Recording in progress.
Yes. So what is that you need to know from this part is resonance circuits have a variety of applications. For example, in the tuning mechanism of a radio or a TV set. See, now you are missing these things physically. Earlier, we used to have knobs. Old TVs, we used to have knobs to change the channel and to fine tuning. We used to have a wheel-like arrangement around that knob. Now everything is happening in the remote. Electronically, you are doing it. Earlier, we used to do all these changes mechanically. The antenna of a radio accepts signals from many broadcasting stations. The signals picked up in the antenna acts as a source in the tuning circuit of the radio, so the circuit can be driven at many frequencies. But to hear one particular radio station, we tune the radio. In tuning, we vary, in fact, the capacitance of a capacitor in the tuning circuit. Suppose in some situations where this is not possible, they will change inductor. How they will change inductor? Suppose if the inductor is filled with an iron rod, for example, if it is fully filled, or if it is partially filled, if it is half filled or quarterly filled, what will happen in all these cases? The L will change. In that case also possible, but majorly we will change capacity. Right. So, in an electronic circuit, what they will do is they will have different capacitors on the board. By just changing the instruction, it will take different paths. Electronically, it will take different paths. Right. When this happens, the amplitude of the current with the frequency of the signal of a particular radio station in the circuit is maximum. Now, what is happening over here? It is important to note that the resonant phenomena is strictly exhibited by L and C combination only, not LR, not CR alone. Whenever, that is the reason why I said when you asked about capacitor, I said wait. When you asked about inductor, I said wait. Now I am telling you, this is the use. Any oscillator, any EM wave emitting source, what you have, it must have an arrangement. Only then you can change that. Okay, right. So which means you cannot have resonance in a RL or RC circuit. It means you can expect some questions, theory questions like this. Next. Fine. Right. Yes.
I by L minus I by from C into lecture.
క్వశ్చన్ నువ్వు ఆన్సర్ బాగా చేస్తావు నెగిటివ్ వల్ల అసలు ఎక్స్ఎల్ మైనస్ ఎక్స్సి టర్మే ఉండదు కదా రిజనెన్స్ అయితే
General.
Okay, right. That is a different discussion which I'm planning to do later on. But anyway, since you questioned me, remember. That's the resonance part. Right. See, try to please understand this is the resonance part. This part of the circuit, it behaves purely capacitive. This part of the circuit behaves purely inductive. If we are asking somewhere here Z, I'll simply write XC minus XL square or XL minus XC square. But whatever happens, it's a square. How can that be negative? Don't say Z negative. Z, you are expressing it as a complex number. You are worried about the magnitude of the Z. Right. Now, please, this is a very famous question in mains. Even it was a situation every year, one of the student might get an opportunity to interact with such person. Try to please go through that. At an airport, a person is made to walk through the doorway of the metal detector. Even now, we are doing that in metros also for security reasons. If or she or he is carrying anything made of metal, the metal detector emits a sound. On what principle does the detector work? In fact, whatever that you are entering is you are passing through some coil. When you are passing through a coil, if you are carrying some metal objects, the metal objects will change the inductance of the coil. As a result, till that point, maybe the circuit is in resonance with some standard frequency. Once the circuit deviates from the resonance, an alarm is set that will horn actually. That's the principle. Read the answer given by the NCERT. Metal detector works on the principle of resonance in AC circuits. When you walk through a metal detector, you are in fact walking through a coil of many turns. The coil is connected to a capacitor tuned so that the circuit is in resonance. When you are passing through the metal, when you are passing through the coil bearing some metal in your pocket, the impedance of the circuit changes because L changes. As a result, the current changes. As a result, electronic circuit is so placed such that any changes in the current, it will give a beep sound. And because of that, you will identify that you are carrying something. Right. Now we will work on another term called sharpness of resonance. Sharpness of resonance. So what is sharpness of the resonance? Now already we know at this peak, not peak point, at any point, this is I versus omega graph, you know. Any point, what is current? Tell me. Peak current. Let us speak about peak. Why? Because you cannot talk about instantaneous values. Either you talk about RMS or you talk about the peak. I'm just talking about the peak. When I'm asking about your peak, this is the response for the peak current, voltage by resistance. I'm asking you again, do you have any doubt in this? Any student having doubt on this part? Asking again. Now, when you be at a resonance, what is happening? Omega L becomes 1 by omega C, and hence the maximum current what you will have is V0 by R. Agreed? Boys and girls, agreed? Everyone in this class, agreed? Right. Next. Now, in my I versus omega graph, this is the concern point. And this is the point concerned to angular frequency omega naught. Till this point, any doubt? Now what I am doing is exactly I am selecting a point as I mentioned. So my detectors will detect up to half the maximum power. So I am taking half the maximum power point as one reference. Accordingly, you will have currents. Yes or no? Here, P max is at this point. Exactly half of this P max. Okay, I will have certain current, but that current is possible at two different frequencies. One here, the other here. One during the circuit is in capacitive mode, the other during the circuit is in inductive mode. What is exactly the meaning of capacitive circuit? Maher? What is the capacitive part of the circuit? XC greater than XL. 1 by omega C greater than omega L. Suppose if reverse is happening, it is inductive part. In capacitive nature, current leads voltage. In inductive nature, voltage leads current. Now you have two frequencies. One is omega 1, the other is omega 2. Now, any doubt till this point? No, we will, because see, suppose if my FM station, China made phones, China made FM earlier, now they are not available in market, I don't know. Some 15 years back, when I used to move around Secunderabad station, I used to find small pocket size radios earlier, purely China. FM radios, they are small. One battery, it will run, that's all. At 83.5 FM, it will respond. 93 also respond. If there is any station close by, that also it will respond. Why? Because it do not have a sharp values of reception. Now we will define usually sharp values. So it is like 93.5. Okay, good. 93.7, maybe the power related to that drops below half the maximum value. If anything drops below half the maximum value, our circuit will not detect. Then you won't have that interference. So therefore, we will save purpose, we will choose half the maximum value, half the maximum power. So that consists of two frequencies, right side as well as left side to the resonant frequency. For convenience, we will write these two terms as small delta omega. Honestly speaking, if you question me, catching hold of my shoulder, I cannot say delta omega both the sides is same. This is not a symmetric graph. But for practical purposes, we will assume almost the same. So therefore, we will take omega 1 as omega naught plus delta omega, omega 2 as omega naught minus delta omega. So I had two observations like this. Now, what is happening? We know omega 1 minus omega 2 is a 2 delta omega, and this term is called bandwidth. Lesser the bandwidth, sharper the resonance. అంతే కదా, ఎంత సన్నగా కత్తుంటే అంత బాగా పొట్టలోకి దిగుతుంది. కత్తి షార్ప్గా ఉందంటే అర్థం ఏంటి? రీజన్ అదే కదా, దాని విడ్త్ కన్నా దాని హైట్ బాగా ఎక్కువ ఉందనుకుంటే షార్ప్గా ఉన్నట్లు లెక్క. మరి మీరు పెన్సిల్ చెక్కినప్పుడు కూడా అదే కదా మీరు చూసుకునేది, టిప్ షార్ప్గా ఉంటుంది, దాని రేడియస్ కన్నా ఆ కోన్ హైట్ చాలా ఎక్కువ వస్తూ ఉంటుంది, షార్ప్నెస్. ఇక్కడ కూడా అంతే. సో దేర్ ఫోర్, సో వాట్ ఈస్ ద కండిషన్ ఫర్ I max? So 1 minute. So what I am dealing here is at this point current. At this point current, I know it is 1 by root 2 times of the value here. Only then I square by 2 వస్తుంది కదా, right? This is the condition, corresponds to half max. So now I am trying to work on equating this to this, equating this to this. Right? Sir, you are cheating. Why you have written omega 1 L minus 1 by omega 1 C? That is the part where inductance is dominating. And this is the part where capacitance is dominating. You agreed with these two equations. Please confirm again. Everyone in the class. Everyone in the class. Everyone in the class. Confirm whether you are agreeing these two equations. Yes or no is the only option for you. Bano, yes or no? Clear. Now what is that I am going to do is, here properly do the squaring part. You will get one expression like this. You will get one expression like this. Omega 1, already I know it is omega naught plus delta omega b. I have substituted like this. I have substituted. Now, one thing is very clear. Finally, I am going to prove delta omega is R by 12. 2 delta omega is R by L. The bandwidth anytime expression is R by L. Unfortunately, in mains, this part is removed. But there is a possibility that even in the removed syllabus also they will ask us. That is the reason why I am giving you all these expressions. I am repeating again, that all this is some simple mathematics which I am not interested. So you can see that I have derived an expression for bandwidth. So how to define sharpness? Sharpness of the resonance is defined as a ratio of natural frequency to that of the bandwidth. Lesser the bandwidth, more higher is the sharpness. So that I have written. This is a very, 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 very important term. Only on this part only you will get lot of questions in mains. And there is another term, the same term omega naught by L. There is another meaning also, and that is called quality factor. The same ratio is having another meaning, which is called quality factor. More high is the sharpness, means more qualitative signal. Now, if you see, this is more sharp, this is a less sharp, this is a less resistance, this is having more resistance. Yes.
మామూలుగా ఆఫీస్ వాడతాం
Ah.
అందులో ఏం చేయడం కలిసి షార్ప్ ఎంత బ్యాండ్
ఏ ఇన్స్ట్రుమెంట్ అయినా రెండు ఉండాలి. అన్ని చాలా ఫ్రీక్వెన్సీస్ అలౌ చేస్తుంది. ఇప్పుడు ఫర్ ఎగ్జాంపుల్ అవర్ అంకిత్ సార్ హ్యాస్ సమ్ డివైస్, యు నో, ఈవెన్ మై మౌత్ పీస్ ఆల్సో ఇట్ విల్ డ్రా సిగ్నల్. It will draw big signal from my mouthpiece also. I think you got my point. So those instruments are sensible enough. There is now I don't think it is available. Some 3-4 years back I have searched in the market. When around 2004-2005, I used to hear radio FM. That's a time when FM was introduced heavily. There is a radio made of China actually, Chibo, KCHIBO. Now it is not available. A small device. You know, it responds and it catches even frequencies, open source frequencies also. See, for example, now cell phone is very almost brought into utility because of unlimited calls and all that. Earlier, it is not like that situation. They used to go for walkie-talkie. Even construction workers also, the base one engineer used to have a walkie-talkie. The top floor another engineer used to have a walkie-talkie. They used to talk through walkie-talkie. Open signal only. For example, when I am broadcasting it, say for example, 83.25. Even if your radio tunes to 83.25, you will hear what they are talking. It's open source. Open channel. Got the point? Right. So all this, you are listening today only. Is it okay? Quality factor also gives the same terms. One nature of, see, actually omega naught by 2 delta omega is called sharpness, and omega naught by R is called quality factor. That ratio is called quality factor. Quality factor ensures more high is the quality factor, better is the reception of the signal. Suppose if we are having signals close like this, less sharp like this, your instrument will toggle between these two signals. Quality will be badly missing. Because try to understand, because that your instrument is having some inabilities, the channel bandwidth is so cost. For example, when I am purchasing from a government of India, a bandwidth of say, for example, 10 megahertz. Okay. So in a bandwidth of 10 megahertz, I need to manage 100 channels. So this 10 megahertz is to be divided by 200. Got the point? You convert 10 megahertz to what you call 10,000 kilohertz divided by 200. What happens? 50. So 50 kilohertz, which means when I broadcast at 2 megahertz, the channel need to be 2 megahertz to 2.001 megahertz is the next channel. Because you had only 10 megahertz bandwidth. I am having only 10 megahertz. So I have purchased between 2 megahertz to 12 megahertz. So I can manage only if I want to make 100 channels in this. Right. So you require how many divisions? Because for safe side, divide it by 200, for example. By dividing it by 200, 10 megahertz, kilohertz, divided by 200, 50 kilohertz, 0.05 megahertz. So if I am leaving 2 megahertz point, my first station starts at 2.05 megahertz. This is the first channel which I will broadcast. Likewise, by the time I reach 12 megahertz, 0.05 minus thing. So you will get my 100th channel. Okay. So now what is the problem? Your bandwidth must be of the range 0.05 megahertz. You should select more qualitatively that this is happening. If your bandwidth is 0.1 megahertz, what happens? In that range, I might be broadcasting nearly some 10 channels. 10 channels. So, same bandwidth 10 channels, and it is like a fish market. So, which is not practically useful for you. Right? So, this is all introduction to LCR series circuit. Now I am going to give you hardcore theory, one more area, and these are two very important area. Already I have done discussion, but still you require these two. After this, we will start doing problems. Remember, this is a very, very theory point. Theory side, very important point. What is that? Wattless current. Even though I have just introduced, I want to give it much more briefly. In an AC circuit, can we have negligible power consumption but a significant current? That's the question, which is not practically possible in a DC current. And that is the reason why I told you n number of times why power lines are sent with why the power lines are with high voltages, not by high currents. I said I square R. I square R factor makes a crucial role. That is the transmission loss. So we should minimize that loss. So therefore, we will send it with the high voltages to maintain low currents. But in an AC circuit, can we have a negligible power consumption but a significant current? Yes, a circuit can have a negligible resistance, but it can have a reactance. No? For example, you take only LR. Okay. Then what happened? If R is very, very, very small, almost tends to 0, power factor is pi by 2 and power loss 0. Such a current is called wattless current. Right. Already demonstrated. If you want to, please go through again. So in a DC circuit, if you wish to change the magnitude of the current, what you will normally do is, you will change the resistance of the circuit by a device called rheostat. But it is basically a resistance-based device which involves loss of energy. Right. Whereas in AC, like you see, now you just go through that. You have a bulb. Suppose you have a DC source of 12 volts and a bulb designed to operate at 6 volts. You cannot connect the bulb directly to the source because it requires a maximum drop of 6 volts here. So it requires a minimum 6 volts, someone to take that drop. So you require a resistance. As a result, what is happening? Even though your purpose is to lit this bulb, glow this bulb, but the problem is we are wasting enormous amount of energy in the form of heat by passing current through that resistor. This is DC situation, which is inevitable. Right. Whereas, okay, same thing. That's what I have introduced. Rheostat, same situation. Whereas in AC, there is a provision. Like, for example, this is the bulb. You want to increase the brightness or decrease the brightness. L is in your hands. Suppose if your source is fixed, you don't want to change omega. L is in your hands. By increasing the value of L, by increasing the value of omega L, by increasing the value of Z, you can reduce current. By reducing the value of L, by reducing the value of omega L, thereby reducing the value of Z, thereby increasing the current, you can increase the brightness of the bulb. Except the bulb, rest all there is no loss. Any doubts? Please go through this. Mains-based theory questions. These are attractive for mains-based theory questions. So we avoid unwanted energy loss in AC circuits while regulating voltage or current by using an inductor coil in place of a resistance. In fact, rheostat, in the place of rheostat. Such an inductor coil having small resistance, almost ideally 0, is known as a choke coil. Now almost we are using LEDs. Earlier we used to have tube lights, fluorescent. In that we used to have these choke coils. గడ్డలాగా ఉంటుంది డస్టర్ లాగా పాత ట్యూబ్ లైట్స్ కి రైట్ known as a choke coil. It is commonly used in tube lights used in house. Remember, this is some theory which is some 30 years old. You are learning that, where you can't even imagine what is that. మీలో ఎవరు బల్బ్ అయితే చూసుంటారు కదా, ఫిలమెంట్ బల్బ్స్ లిటరల్లీ చూసుంటారు. మీరు చూసారా? ఆల్మోస్ట్ LEDs are available in the market. Right. Household power supply is 220 volts, 50 hertz. If we connect a tube light directly to this supply, it will get damaged. To reduce the current and enhance the voltage across the tube light, we connect a high inductance, higher value of L, low resistance choke coil in series. Okay, so what is the impedance? The impedance is under root R square plus omega L square. Just now we had. What is current? Voltage by Z. Voltage by under root R square plus omega L whole square. So major drop will be at the choke coil. Still the current pass through the bulb. You will have the required brightness. So conclusion step is we have successfully reduced the potential difference across the bulb, in this case resistance, by increasing the impedance, but it does not result in any extra energy loss as the inductor does not consume power. Okay, the same question.
ఇండక్టర్ అయితే DC కరెంట్ ని ఫాస్ట్ కింద చేస్తుంది, అదే కెపాసిటర్ రాస్తే AC కరెంట్
Yes, exactly.
DC కరెంట్
అవును, లో ఇండక్టర్ వాడతాను లేదా డిపెండ్స్ ఆన్ ద కేస్. Try to please understand, in every LC there is inductor. Current is passing, it opposes, that's all. Suppose if we are using a very low L, it almost has no effect. A very high L, the current almost drops to zero. You are using very low C, same situation, right? And to answer these, I have prepared two questions earlier, which I would like to answer it right now. Please go through this question. This is also from NCERT. Everyone try to please go through this question. A light bulb and an open coil inductor are connected to an AC source through a key as shown in the figure. You can see that figure 7.11. NCERT diagram. The switch is closed and after some time an iron rod is inserted into the interior of the inductor. The glow of the light bulb, what happens? Now the question is, you are inserting an iron rod into that coil. What is the consequence of this change? L increases. As L increases, Z increases. As Z increases, current decreases. So the glow of the light bulb decreases. One more important. Yesterday also, I wish to discuss this. Please go through this. A lamp is connected in series with a capacitor. Predict your observations for DC and AC connections. What happens in each case if the capacitance of the capacitor is reduced? You are connecting a lamp in series with a capacitor. Good question. So if it is an RC circuit and the place of bulb, imagine the resistor. You have a capacitor like this and you have a battery like this. Right. You know, in an RC circuit, the current is high initially, zero finally. So what happens? Initially the bulb glows higher, finally the bulb glows to zero. Now the question is, now you have when a DC source is connected to a capacitor, the capacitor gets charged and after charging no current flows in the circuit and the lamp will not glow. There will be no change even if C is reduced with an AC source. There will be no change. The lamp will not glow. Clear? Right. Now, a question is predict your observation for DC and AC connections. There will be no change even if C is reduced with AC source. Why? DC. No, see, try to please understand. In case of DC, makes no difference. Maybe initially there may be effects. Otherwise, after which there is no effect, the bulb will not glow at all. That's all. Whether it is C, 2C or C by 2 makes no difference in case of a DC. Now I am using an AC. See, the change of C affects XC. The change of XC affects Z. The change of Z affects current. And the change of current affects the glow of the bulb. So as you increase C, XC decreases, Z decreases, current increases, and hence the bulb shines brightly than before. But take care, the drop across the bulb never exceed its operating limits. Right. Okay? Clear? Sure? Any doubts, boys and girls? So I have just introduced the basic and necessary theory to do questions. Right. Now we will do some basic questions.
Basically situations లో resistor approach resistance ని drop ని approach inductor లేదా capacitor కి మారుస్తుంది.
Now try to work on this question. Everyone try to work on this question. So basic theory is done. Now what we need to do is, what is your doing? Don't have any. Basically, necessary basic theory required to run the show I am given. Now we will work on problems. Right. Let me work on this. So quick questions. We will work very fast. A plate on the back of a personal computer says it draws a 2.7 amps from a 120 volt 60 hertz relay. Don't worry, this is US. For them, 120 volts, 60 hertz. So therefore, no issues. There is nothing to fight here. Their choice. Right. Now, the question is, what is the average? What is that they're asking for? I hope everyone in this class have understood. They're simply asking average value, RMS value, and the average current from a positive half cycle and average current from a full cycle. First thing, for D, the answer is 0. Most enjoying part of the question. 80. I average is 2 I naught by pi. RMS I naught by root. That's all. So the 2.7 amps, what they have given is IRMS value. What they have given, the IRMS value is 2.7 amps. Okay, what do you want? What is the average value of the square of the current? Andagane ippudu what is that they're asking? The square value of this. So this will ఎందుకు బయట who is asking I not for you? No one is asking that. ఇదంతా 5 7 7.3 at the boundary. Ampere square. Current amplitude. I naught is equal to 2.7 root 2 amps. This is the current amplitude. Average current. The average current is 2 by pi times I naught. 2.7 into root 2 amps. I've done completely everything. Okay, it's like a trial ball. When we are playing, it is like a trial ball. An alternating current is given by the following equation. I is equal to 3 root 2, 100 pi t plus pi by 4. Find the frequency. Area frequency omega is equal to 100 pi. Frequency is omega by 2 pi. So obviously this will become 50 hertz. RMS value. IRMS is I naught by root 2. It is simply 3 amps. Right. Next. Which of the following two waveforms has a higher average value is what you are asking. Average ante area ne kada. Area in the first case. Area in the first case is equal to half V naught T. So I average into 2. Repetitions only half cycle తీసుకోలేదు. So I average is V naught by 2 in the first case. In the second case, 1, 2, 3. T by 3. Andega. So area 2 is equal to half into V naught into T by 3. Then you will divide it by T by 3 only. So what is I average? V naught by 2. Both the occasions it is the same. Any doubts? ఎందుకు తీసుకోవాలి? Only half cycle. There is no half cycle in both the cases. It is everything repeated. Same. ఎన్ని తీసుకున్నా అంత వస్తుంది. అందుకే యావరేజ్ అన్నారు. ఆర్ఎంఎస్ ప్రస్థానం చేయాల. We will take these చిన్న క్వశ్చన్స్ కాకుండా కొంచెం పెద్ద క్వశ్చన్స్ చూద్దాం. రైట్. 6th question. What exactly does this term mean here? In the circuit shown, the frequency of the source is adjusted so that the reading of the AC ammeter is maximum. The inductor shown is a short coil in a vertical orientation. A steel ball is dropped through the coil. How is the reading of the ammeter affected when the ball enters the coil? L decreases. L increases. Z అవుతుంది. No. What is the initial condition? Initially circuit. Already we have done this. Even I have just seen that. Not there? No issues. How is the reading of the ammeter affected when the ball enters the coil? L changes. So in fact, L increases Omega L increases. So Z decreases. No, Z increases. Z increases. So I decreases. The ammeter shows decrement in the previous reading. So long the ball is in the coil, reading is low. Any doubts? Boys and girls, any doubts? Right. ఏ ప్రాబ్లం చేస్తున్నా చెప్పు సరే నేను మార్చేయాలి నెక్స్ట్ you work on this question. Everyone try to work on this question. And a lamp, just now I taught you this. A lamp L is connected to an AC source along with an air core inductor, as shown in the figure. How is the brilliance of the lamp affected if you are using iron is a good ferromagnetic material as far as I'm very good on iron, that's for sure. So kabatti meeku em avutundi ante L increases, Z increases, current decreases, so brilliance decreases. Any doubts? Any doubts again, once again, please. Right. Next, copper diamagnetic parana? Diana, right? Copper, gold, silver, మూడు డయానా అనుకుంటా నాకు గుర్తుంది అన్ని విలువైనవి డయానే అందుకే అది ఎంత అడ్వాంటేజ్ అంటే మ్యాగ్నెట్ కి అతుక్కుంటే అది రోల్డ్ గోల్డ్ అని ఈజీగా తెలిసిపోతుంది. So therefore, in case of copper, L decreases, Z decreases, I increases, brilliance increases. L తగ్గుతుంది ఎందుకంటే you are negative that. You are negative కాదు, susceptibility negative. 1 plus susceptibility కాబట్టి less than 1. Earlier it is at least 1 or more than 1. Now it is less than 1. When compared to the previous condition kada. Earlier if 10 lines are going, now no line will pass through. Right. Iron sheet pasted together with the insulation in between, laminated iron core. Laminated iron core. Why they are using this term means because of lamination, eddy currents are avoided. Iron sheets pasted together with insulation in between, so it will avoid eddy currents. So not much of effect is there. So therefore, when compared to air, I can say no, 1 minute. Don't say like that. When compared to an iron rod as a whole, little less, but still better than diamagnet. I still iron. Still iron. So కాబట్టి again iron laminated iron core.
ఐరన్ షీట్స్ అంటే అట్లా ఎట్లా పెట్టారు
This portion is placed inside.
షీట్ ఇండక్టర్
Red color part insulation.
షీట్ ఇండక్టర్ ప్యారలల్ గా పెట్టారు
ఎందుకుండదు ఇలా పెడతా నేనండి డాక్టర్ ఎలా పెడతారని షీట్స్
ఇలా కూడా పెట్టచ్చు అంటే తేడా ఉండదు కదా ఐరన్ రాడ్ కి ఐరన్ షీట్ మళ్ళీ రెండు ఇచ్చడం
hardcore iron number of lines is high when compared to the laminated. So కాబట్టి laminated iron core. Now tell me in which case the lamp will be least bright. Sure. Think again. Undoubtedly copper, it is okay. What you suggest? ఎడ్డీ కరెంట్స్ ఆస్పెక్ట్ ను కూడా కన్సిడర్ చేయాలి. స్టడీ కరెంట్ లో ఐరన్ అన్డౌటెడ్లీ ఇస్ ద బెస్ట్ చాయిస్. ఆల్టర్నేటింగ్ కరెంట్స్ లో ఐరన్ కూడా చూస్తుంది, బట్ డామినేషన్ అంత ఉండదు కదా మెయిన్ కరెంట్ కన్నా.
ఎఫెక్ట్ చాలా ఉంటుంది అంటే కరెంట్ మారుతున్న కొద్దీ ఆ ఎడ్డీ కరెంట్ కూడా మారుతున్న కొద్దీ అది కరెంట్ ఇంక్రీజ్ చేయాలని చూస్తూ ఉంటుంది ప్రతిసారి. ఆ లాజిక్ వేస్తే సి
ఓకే, బట్ దే హావ్ గివెన్ లామినేటెడ్ ఐరన్ కోర్. ఆన్సర్ సి ఇచ్చారు. బట్ మనం మీరు చెప్తున్న దాని ప్రకారం సిఏ వచ్చింది. ఏ చెప్పావు కదా ఐరన్ పెడితే నువ్వు ఏనే చెప్పావు. బట్ దే హావ్ గివెన్ is okay. Right now I'll just hold. I'll work on this and I'll inform. Yes. Question number 8. In the circuit shown in the figure, the voltage across the resistance are box A, box B represented like this. Find the phase difference between current and the applied voltage. First of all, VR, and obviously VR. VA. VB. Any doubts? I have done the question. These are my phasors. VR, VA, VB, V. It already root 2V. మళ్ళా ఇంకో root 2V వస్తాను మీకు. So the resultant phasor is 2 root 2V. And this is how you will have current. This angle is 45 degrees. Find the phase difference between current and the applied voltage. 45. Any doubts? Any doubts? I'm asking again, any doubts? Any doubts? Go through. సాంకేతిక ఇప్పుడు అడిగితే తప్పేమీ లేదు, ఎందుకంటే మనం కావాలని ఆగి అందరినీ స్టడీ చేసి నెక్స్ట్ వెళ్తాం. 20 minutes తర్వాత వెనక్కి వచ్చాము, అది తప్పు. ఎందుకు ఇంత టైం ఎందుకు వేస్ట్ చేసినట్టు మనం? రైట్, నెక్స్ట్. Shall we go for the next question? Clear? In the series circuit of the figure, suppose R is equal to 300 ohms, L is equal to 60 millihenry, C is 0.5 microfarad, source amplitude is 50 volts, amplitude, not RMS. Omega is given. నువ్వు ఏది ఇచ్చినా నేను చేసేది ఒకటే. వాట్ ఈజ్ ఒమేగా ఎల్? ఒమేగా ఎల్ is 1 into 10 to the power of 4 into 60 into 10 power minus 3. 600 ohm. 1 by omega C is 1 by 1 into 10 power 4 into C, half into 10 power minus 6. 200 ohm. Yes, circuit. ఆగండి. What is this circuit? It is the nature of this circuit. No, Shreyas. Inductive. Ventalla. XL greater than XC. So this is inductive. ఇంకేమన్నా అయిపోయిందా యాక్చువల్లీ? ఫర్ ఎగ్జాంపుల్ రెసిస్టెన్స్ ఎంత అండి? వాట్ ఈస్ రెసిస్టెన్స్? 300 ohms. సో ఫైనల్లీ XL minus XC, which is equal to 400 ohm. $300 ohm. This is 53 degrees. Any doubt till this point? So what is the conclusion that you can make? Conclusion. Conclusion. ఇంకా నా పాయింట్కి రావాలి. వోల్టేజ్ లీడ్స్ కరెంట్ ఫస్ట్. అడిగాడు కదా ఇక్కడ క్వశ్చన్స్. V leads I by 53 degrees. XL determined, XC determined, Z determined. Z is equal to root 300 square, 400 square, 500 ohm. What is the current amplitude? Current amplitude is voltage amplitude by Z. 50 by 500. 1 by 10 amps. Phase angle, everything I have determined. వోల్టేజ్ అరే ఏముంది ఐ ఇంటూ ఎక్స్ఎల్ చేస్తే అక్కడ ఐ ఇంటూ ఎక్స్సి చేస్తే ఇక్కడ ఐ ఇంటూ ఆర్ చేస్తే అక్కడ ఎనీ డౌట్స్ ఎనీ డౌట్స్ ఎనీ డౌట్స్ 3 సార్లు అడుగుతున్నారు రైతు చెప్పరు ఫేజ్ యాంగిల్ అంటేనే మీనింగ్ అదే time dependence of instantaneous voltage in first of all చెప్పాలంటే ఏదో ఫంక్షన్ ఇవ్వాలి ఓకే we assume అని ఇస్తే దాన్ని బట్టి మిగతా సే what is the current through the what is the current through the resistance? The current through the resistance is I చెప్పేసాం కదా 1/10 times R. IR is I naught sin omega t wrong. Yes, because ఇది ఈ కదా ఇది ఈ కదా I naught sin omega t అగర్ ఆపరిస్తాం అంటే you want the current through the inductor కదా ఒక్కడగా దొరుకుతాడేమో అనుకున్నా కాసేపు ఆపలే because series so VR is I naught or sin omega t minus 53 degrees. VL is I naught XL sin omega t minus 53 degrees plus pi by 2. VC is I naught XC sin omega t minus 53 minus pi by 2. Any doubts? Ram Karthike, do you have any doubt? Any? Sir. is relations. నవ్వు చేస్తున్నారేమో డౌట్ గా
Recording in progress.
అయితే అక్కడ పోయింది. అయినా ఆపాలి, అంతసేపు చేయలేదు, అది ప్రాబ్లం.